Today we are going to prove that the square root of 2 is irrational by exploiting an even-odd contradiction. That is to say, we are going to show that the supposition that the square root of 2 is rational entails that an odd number can be equal to an even number. So we suppose that the square root of 2 is equal to p upon q, where p and q are both natural numbers whose greatest common divisor is 1. That is to say, they're relatively prime, so that the fraction p upon q is in its lowest terms, and then we square both sides of our statement root 2 equals p upon q, and we show that 2 equals p squared upon q squared. And so multiplying both sides by 2, we find that this entails that 2q squared equals p squared, which entails that p is even. And if p is even, because the greatest common divisor of p and q is 1, q must be odd. And so if p is even and q is odd, we can let p be 2r and q be 2s plus 1, where r and s are members of the natural numbers. And we now tease out the implication of our statement that 2q squared equals p squared, where p is even and q is odd. And so we can see here that 2q squared equals p squared is the same as saying that 2 lots of 2s plus 1 all squared is equal to 2r all squared. And if we expand the brackets, that means that 2 lots of 4s squared plus 4s plus 1 equals 4r squared. And if I divide both sides by 2, I discover that 4s squared plus 4s plus 1 equals 2r squared. And if we look at our final line of working, if I factor out the 2 there, I've got 2 lots of 2s squared plus 2s plus 1, which is the same as the left-hand side, which equals 2r squared. S is a member of the natural numbers, so that 2s squared plus 2s is a member of the natural numbers. And so on the left-hand side, I've got 2 times an integer plus 1, which must be an odd integer, and that has to be equal to an even integer, 2r squared, if the square root of 2 is to be rational. And so we show by contradiction, an even-odd contradiction, that the square root of 2 is in fact irrational.